Okay, and we're back with part 2. And so, continuing on from this definition, let's do, well, a quick recap. Um, we defined we defined the sum of two subspaces of a vector space V as such. That is, all the elements U1 plus U2, such that U1 is in big U, U1, and U2 is in big U2. Okay, and now we provided the following proposition. That is that the sum of these subspaces is the smallest subspace of V containing all of those subspaces. And so this is actually kind of, well, tricky because this is a multi-step proof, although it might not seem like it is. In fact, there are 3 parts. First of all, we have to show that it is indeed a subspace of V, but also that it contain. First of all, yes, it is indeed a subspace of V. Also that it contains all of these UIs, indeed contains all those UIs, and finally that it is the smallest such subspace. Okay, so let's do the first part. Okay, it is indeed a subspace of V. Okay, so we look at the values. First of all, let's see if the identity element is there. So we have U1 plus all the way to UN equals 0, question mark? Yes. Just take each of the UIs to be 0. Since all of these are subspaces, the identity element must be in those sets. And so take UI equal to 0, and 0 plus etc. 0 is indeed 0. So that check mark. Additive identity, just as easy. If we take U1 through UN, U1 plus UN, that's a member of the subspace S, plus U1 prime all the way to UN prime. If we rearrange this, we can actually write this as U1 plus U1 prime. Again, this is by generalized associative property, and you can prove it by induction. UN plus UN prime. And so, since, again, these are subspaces, we can write each of these U1 plus U prime. Both of these elements are in U1, the subspace U1, and so this element is in U1. Same thing goes for each of these elements. So that is U1, this is in UN, and so this is indeed in our subspace. We'll call it S, okay, just for convenience. Okay, that's good. And now finally for the scalar multiplication, well, this is just as easy. If you take an element here, multiply it by, say, lambda, so lambda times this, distribute it through by distributive property, you'll get lambda times U1 plus dot 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 lambda times UN. Each of those little summands are going to be a member of U1 all the way through UN, since they're all subspaces, and so indeed we'll also have that the result is an S. So now on to the second part. Now what we must show is that indeed all of the UIs are actually in the subspace. We just showed it's a subspace. And so that's not too hard. Consider the sum, but to form UI, the subspace UI, simply take the sum. Again, it's the sum of all of these, ranging through all of the possible values of U through UN. and then set each of these values equal to 0 except for UI, little ui. So all the way to ui plus 0 plus 0. You get the picture? And so clearly this is an element of this of S. So this is an S, and we can range through all of the UI, and so indeed UI, each UI is an S. Alright, good. And finally, we need to show it's the smallest subspace. Well, not too bad. Suppose a subspace T contains, so let's say U1, each of the UIs are contained in T, which is a subspace. Well, since it's a subspace, it needs to contain the sum of all of the elements. Well, how do we word this? Since it's a subspace, if we take every element U1 through UN, the sum of all of these elements, it's closed under addition, right? So the sum of all these elements must be in T. And so if we range through all of the possible elements U, which have to be in T, then, well, we get that. This implies that S is inside of T, and that's QED, because that means that S is the smallest such subspace. Good. Now we're ready to be even more particular. We won't be working with sums as much as what I'm about to say here, which is an even more particular version of sums, of subspaces. That is the notion of direct sums. So, definition: a direct sum of U1, two subspaces U1, U2 in vector space V. We say that it looks like this, so it's a plus sign with this kind of circle around it, equals, well, those look like V's, I'm sorry. This equals U1, U2, so all values U1, U2, again, such that U1 is in U1, U2 is in big U2, so this has the restriction that each element in U1, U2 can be expressed uniquely as the sum of two elements in U1, and so this is a wordy definition, but really it's not all that hard, because so let's say U1 and U2 are two elements in U1 and U2, then we can't have that, and let's say S is in U1, the direct sum with U2, then, so let's write it out. Then we cannot have U1 plus U2 equal s, but also another, so u1, u2 prime equal s. So these are two unique ways of writing s as the sum of two elements, different elements in u1 and u2. So that's not possible. However, a normal sum of two subspaces can have that. Well, there are two examples that we can look at. There's one example in particular, which has, as an added bonus, other examples that go along with it. That is, let's say u1 is simply the set of all lists of this form in F3, such that, I'll just write such that x is in F. Ayo. X is in F. Okay. 2 such that it's another way, such that y is in F field. That's annoying me. Okay. Now these are direct sums. It's not hard to see. I mean, intuitively this is true. Because, well, where u1 has actual coefficients, u2 has zeros. And so, in fact, one can show that this is indeed a direct sum. I'll leave it as an exercise. Okay, but it's if you think about it for a while, it makes a lot of sense. For example, if we have like 2, 1, 0, that's clearly an element of u1 plus u2. It's a direct sum, so we would have a circle around it, but to be less specific. So here, this is an element. Writing it the opposite way around, that's really cursed. But this is indeed an element. We can't write it in another way, as a sum of another two elements in u1 and u2. So, but in general, this is not hard to show. And now we're going to develop a technique for showing these things. Two techniques, one better than the other, perhaps. So let's see. We're going to erase this definition. It's pretty self-explanatory. So these are two nice proofs. Time-wise, 12. Okay, time flies fast. Flies fast. Okay. We might as well get rid of this. It's not very helpful anymore. Okay. So now we're going on to two important results. Okay. Suppose, yes. So here's one important result. That is that the sum, let's say u1, again, u1, u2 are, I don't like this notation, but we're going with it, are subspaces of V. Then u1 plus u2 is, I don't know why I'm writing it like this. u1 plus u2 is a direct sum if and only if zero, how do we word this? Oh yeah, if and only if yeah, we'll write it in a compact way. u1 plus u2 equals 0 implies that in fact, do we want to generalize this? Like, this is the difference between these two results, is that one can be used by looking at the sum of multiple subspaces, while the other can only be used if you're looking at the sum of two. So in fact, this can be generalized. Un plus etc. where I left out saying that these are each in u1 to un respectively, implies that each ui is equal to 0. So let's prove that. First direction, this is quite simple. If it's a direct sum, 0, which is surely an element of this sum, because, well, we showed it's a subspace. Since it's a direct sum, that means that 0, which is in that subspace, can be written uniquely. But surely one way to write 0 always is as the following. That's one way, because 0 is in each of these subspaces, and so no other way exists. No other way. By definition, by the fact that it's a direct sum. So that was quick. And again, I left out a lot of writing on the board. Other direction. So, let's see. We could go with the contradiction. But, yeah, why not? By way of contradiction, suppose not a direct sum, then 0, well then any element in that sum, call it S. S is in U1, UN. S can be written in two different ways. Then S can be written as U1 prime plus etc. It can be written in these two different ways, since it's not a direct sum, where each of these, where U1 is not equal to U1 prime, etc. And subtract these. Subtract, this gives us 0, it's a good sign, is equal to U1 minus U1 prime plus etc. UN minus UN prime. Now let's use what we're assuming in this case, which is that, well, first of all, these subtractions all take place in the subspace U, U1 through UN respectively, and so since they're subspaces, these are in U1, UN, okay, etc. And so using this proposition, I'm using the assumption, this equaling, these are all, we can treat these as U1 through UN. These equaling 0, the sum of these equaling 0 implies that we have in brackets here, this equals 0, and etc. through this equals 0. So, in other words, U minus U1 prime equals 0, so U1 equals U prime, U1 prime, etc. through U1 equals UN prime. So that checks the theorem. That's exactly what we wanted. That's a contradiction. I guess I should point that out. Contradiction. Hence, that proves it. Since we assumed these were different. Okay. So that's this. Whoa. Okay, that's this result. Having fun with this. It's fun to do some proofs, right? Leaving out most of the examples. That's what we do here. Next result. U1, I'm going to leave out all the extra stuff. U1 plus U2 is a direct, again, these are subspaces of V, direct sum if and only if U1 intersect U2 equals just the 0 element. Okay, let's prove this. In other words, the only vector in both U1 and U2, the only vector in both U1 and U2 is 0. So let's prove this. I haven't written proof out. I'm just going to write it this time. Proof. We're going to write out the full word. This deserves to be written out. Proof Okay, first direction, suppose it's a direct sum. Then we want to show that the only element in there is 0. This time we're going to mix it up. We're not going to use contradiction, but it's the same kind of strategy. Take any element, again, let's use S in U1 intersect U2. We want to show it's 0. Clearly, since it's so we're looking for a contradiction if it's non-zero. So take elements in U1 plus U2. That would be U1 plus U2. Well, we can write S in two ways. Well, two ways, okay? S can be written in two ways. You want S plus 0, but also it can be written as 0 plus S, where this takes place in U1, and this takes place in U2. That's the difference here. And so, in other words, we can write S, which is, of course, a member of U1 plus U2, this sum of subspaces, in two different ways. Hence, that would contradict the fact that it's a direct sum. Okay? And so, unless S is 0, because then these two representations are the same. And so, that proves the first direction. Okay. Second direction, converse. Let's suppose this is the case, and we want to show that U1 plus U2 is a direct sum. Okay, well, let's look at U1 plus U2 equaling 0. We want to show that this implies that U1 and U2 are both equal to 0 by the previous proposition, by the previous result, right? So we're using that result. Well, this implies that U1 equals minus U2. Okay. Now, since we're dealing with subspaces here, U2, so U1 is in U1 by definition, of course. That means that minus U2 is in that means that minus U2 is in U1, the subspace U1. And so, since it's a subspace, scalar multiply that by minus 1. And so U2 implies that U2 is in capital U1. Therefore, this is weird because now we have that. Now we have that both. Now we have that. Well, let's see. U2 is in both U1 and so U2 is in U2. So it's, in other words, U2 is in U1 intersect U2. But that's a contradiction if U2 is non-zero. If U2 is non-zero. But since it is, well, let's backtrack here, being pretty vague. We're using this fact. The intersection is only the 0 vector. And so if this is non-zero, if U2 is non-zero, then we get a contradiction. And so we need to have U2 equal 0. And so therefore, U1 equals 0. And that proves this result. Okay. And I believe that's it for the important results for section 1 of the book. I'll just double check. Here we are. That's pretty much it. Look through it again. Yeah, I think we covered everything. That's great. Book uses different notation than me. Who cares? Okay. So in the next video, we're going to start covering section 2, section 2a, and that will be on finite dimensional vector fields. There are going to be many interesting proofs in there, and so yeah, be prepared for that. I'll see you then.